reporting out of this. Close. It goes over there. Alrighty. So here's our summary quiz. And so if we talk about heat flow, heat is never going to go from cold to hot. If you have a system, hot energy always gets absorbed by a cold system. Just like how things always diffuse from a high concentration to a low concentration. Energy always transfers from a high temperature to a low temperature. This formula, you know that. I'm not even going to go with that one. That's our Q1. On this one, we have a 15-gram sample, and it's absorbing this amount of heat, and its temperature increases to 25 degrees Celsius, and we want to know the specific heat capacity. So I'll put this one up on the whiteboard. Alrighty, let me get my screen back. So grams is always going to be our mass. So we know that M is 15.1 grams. They tell us that we're absorbing heat, so that's our Q. Q is heat absorbed. If we check the notes, it's in there. 48.75 joules per gram Celsius. And our temperature increases by 25 degrees Celsius. So if they only give you one temperature, they're just giving you delta T. They're not telling you to find it. They're just giving it to you. And they want to know what mass. No, what's the specific heat? They don't know the specific heat. So you set this up. Q is MC delta T. 48.75 is equal to 15.1. We don't know C. 25 degrees Celsius. And then you solve for C. Here's our variables. There's our formula. And then I have confidence that you know the algebra to solve for the unknown right there. So if we look at number 5, they tell us that we have a piece of aluminum and it's heated up to 275 degrees Celsius. So we'll call this the aluminum. T1, 275 Celsius. And we stick it in 200 grams of water, so we'll put the water over here. So our mass is 200 grams. And the initial temperature of the water is 25 degrees Celsius. And at the end of it, when we combine them, our final temperature is 50 degrees Celsius. And we want to know what the mass of aluminum that we started with. So I'm telling you that the C for water, we're going to use 4. And C for aluminum, we gave you 0.9. And so now we have mass, change temperature C, change temperature C, we don't know mass. So if they give you a bunch of variables, the best thing to do is just kind of outline them out. So this is number 5. We don't know the mass of the aluminum. They give us T1, they tell us final temperature, they tell us the specific heat. We put it in 200 grams of water. Here's T1, T2, specific heat of water. So we plug it in the formula. So the aluminum starts off hot and gets colder, so it's losing heat. So this is negative Q lost. Versus the water is gaining in temperature, so this is our Q gain. So we'll have negative, mass we don't know, C, and change temperature. 50 minus 275. And plug everything in on the other side. We have our mass, 200 grams. Our C is 4. And our change in temperature, T2 minus T1. So here we have our negative Q lost and Q gain negative because it's losing energy. And it'll cancel out when you change the temperature. And then you multiply all this together and then solve for the mass right there. Let's see, let's mute this one. Unmute this one. Alrighty, shall we continue and talk about the harder ones? Hey! Alrighty, go back. Let's see, I'll go here to look at that image a little bit larger. Internet seems to be a little laggy today. Alrighty, so we want to know. Right over here. What occurs when the catalyst is added to the chemical reaction? So does A change? Does B change? Does C change? Or does D change? So our activation energy, because a catalyst lowers activation energy, is the point from our reactants to the peak. So our catalyst is going to lower this peak down, which is going to change B. It's not going to change A. So A is an option, B is not, C is not, and D is not. So in changing B, we're also going to change C. We can use process of elimination instead of, I think that would be the easiest way to go about it. So if we think about the next one, the area under these curves is equal. So there's the same number of molecules under each curve. And just to be even more sure, both samples have 100 grams of water. So they both have the same amount of molecules. But sample 1 is at T1 and sample 2 is at T2. And we want to know, compared to sample 1, sample 2 contains. So which one of these is true about sample 2? So do the molecules with a lower average kinetic energy? So does sample 2 have molecules with lower kinetic energy? Well, we know the number of molecules is the same. It looks like they actually have higher kinetic energy because the T2 line falls further on the energy scale. Molecules with lower average velocity. So if they have high energy, do those molecules have high or low velocity? Are they moving quickly or slowly? They're going to be moving quickly. We have more molecules with enough energy to evaporate. Well, if this is considered our energy needed to evaporate, because that's where it says right here, activation energy is the energy needed to evaporate. Temperature 2 does have more molecules with enough energy to evaporate, so that one would be true. Total molecules, it says at the very top, they have the same number of molecules under the curve. And we have the same mass, which should be the same amount of molecules. And then this one, I'm not going to go over because that should be easy. Remember, exothermic ends in low energy. Any other questions about the quiz before I go over the simulation real quick? Alrighty, so I'm going to go through this one again because I might have done it a little quickly or rushed before. Let's see, assignments. I'm going to hit that URL right here. And then we're going to hit play. Then we're going to hit intro, and then we're going to check the boxes for energy symbols and link heater. Intro, energy symbols, link heater. So then we're going to go through part 1 and part 2. So we should be able to describe how does energy flow from hot to cold, and what's specific heat and what does it mean in terms of the number for specific heat. So we're going to put oil and water over heater, and we're going to drag a thermometer. Water, oil, thermometer, thermometer. Now we're going to add heat. So we'll add heat 10 times. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So after 10 times, the water went up 1 little degree on here, and the olive oil went up a little more than 1. So let's do 10 more times. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So after 20 increases of heat, the water went up a little bit over 2, and the olive oil is all the way up to 3. And we see energy leaving our liquid. So when liquid particles get high energy, they go from liquid to gas, and we call that evaporation. And so our heat is going from the heat source to the system, to whatever is absorbing the heat, in this case the water and the olive oil. So the energy goes from the heat source to the system. And we notice that the olive oil, or the oil I think it was, gets a little bit hotter faster. And as we keep increasing the heat, we see energy starts leaving the beaker. And what happens when that energy starts leaving the beaker is that our liquids are evaporating. They've absorbed so much energy that now they have the potential to evaporate. Any questions before we go do the cold side? Alrighty, I'll open it back up. Let's move you guys over here, and I'm gonna reset it. We're gonna put water, olive oil, thermometer, oil. So now we're gonna make it cold. Energy, link heaters. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that was probably a bad example. I think that they got cold. Our thermometers can't measure how cold they're getting. Let's see if we can heat them up real quick and see a better change in temperature. I'm sorry this is taking so long. Hey, there we go. That works. Now we don't have to do it so many times. So you can hold it down to make it get hot faster. And so then we see how much faster that oil heats up than the water. Hope I can get the water that hot. So now we'll hold it down to cold. And so we see that the energy is going from the hot olive oil and the hot water into the cold ice. So the cold is absorbing the heat just like the cold beaker was. Maybe do I have it open here maybe, and I can just look at it here instead of opening it over and over again. Nope. So when we make it cold, the energy goes from the beaker to the ice. Which one gets colder faster is a little bit hard to answer because the water started off at a lower temperature, so I'll be lenient with that one. And if we keep making it cold, what we should see, let's see if we can see it, in addition to the energy going into the beaker, there it is, there's the energy going down into the water. And so we know that cold absorbs heat. And gases are hot. And in our atmosphere, we have the gas form of water in the atmosphere, water vapors. And so when that hot gas form of a water vapor comes in contact with the cold energy in the system, that cold energy absorbs the hot energy of the gas phase and turns it into a liquid. And so when energy is absorbed from the atmosphere into the system, it's considered condensation because the system is so cold that it's pulling all the gas energy out of the atmosphere and making those molecules liquid. It's slowing them down so much that now that they're in the liquid phase. Does that part kind of make sense? I would say the oil got cold faster because it went like, what? But again, if you say the water got cold faster, I'm not going to take off a whole bunch of points. The observations are your observations. So when we got hot, we gave the liquid particles enough energy to evaporate into the gas. And when we got cold, the gas particles in the atmosphere got their heat energy absorbed into the cold system, and they got slowed down so much that they became liquid, called condensation. That's why you get condensation on a cold glass and not a hot glass. The cold glass is absorbing all the hot energy from the gas molecule, and that's why when your glass starts getting condensation, it's not as cold as it was because it's absorbing all that hot energy from the atmosphere. And I think there's one other part. So we've talked about specific heat being the value of how much heat is required to be absorbed. And so if you need a lot of energy to heat it up, like we did with the water, we even see up on the board that water has a specific heat of 4. It has a high specific heat number. If the temperature changes really easily, it has a low specific heat number. And then we should see this same idea with the brick and the iron. Brick, iron. So we'll heat them up. And which one's gonna get to the top first? It looks like it's gonna be the brick. And then if we make them cold, It looks like it's going to be the brick. So the brick gets hot faster and it gets cold faster. And so if we look at our question, that answers that one. And so the specific heat of the iron is higher. And we usually make pans out of iron. You're like, why would you want to make a pan out of something that takes so long to get hot? Well, the idea is that we saw that it took a lot longer to get cold. And so since it holds on to that heat because it takes so long to absorb it, that if you don't want your food to get cold right away, you'll cook it in an iron pan. It's going to hold on to that heat longer. You can turn the stove off and it'll still be hot in like 30 minutes. And let's say we make a chimney out of brick. Well, the chimney is what warms up our house, so we want it to get hot really quickly. And so, but we don't want to say we want the fire to go out. We don't want the house to be hot all the time, so then we want something that loses its heat very quickly also, so when we put the fire out, it won't be hot anymore. Does that kind of clear up some stuff on the simulation and the quiz? Is there any type of practice problem that you would like me to go over, or any of the other stuff that we've been assigned? Because we are just about out of time, but if you want me to go over something, I can. If not, you are free to go.